Look up at the night sky, really look. What seems like a silent sea of stars is actually alive with motion. A cosmic orchestra playing a symphony we can't hear with our ears, but one that shapes everything around us. Those distant points of light aren't just burning gas. They're vibrating, pulsing with rhythms that ripple across the universe like waves in an endless ocean. This is the unseen symphony of the stars, a hidden harmony that connects galaxies, bends time, and even echoes within the very atoms of our bodies. And today, we're going to listen. For thousands of years, humans have gazed at the heavens, sensing there was more to the stars than meets the eye. Ancient civilizations mapped the skies, believing celestial movements held the secrets of fate. Now, modern science reveals an even deeper truth. The universe isn't just silent and still it hums. Every star, every planet, even the emptiness between them thrums with invisible vibrations, a cosmic soundtrack written in the language of gravity, light, and energy. These vibrations are the heartbeat of the cosmos, shaping the birth and death of galaxies, guiding the dance of black holes, and weaving the fabric of space itself. But how does this symphony work, and why does it matter to us here on our tiny blue planet? The answers lie in the delicate interplay of forces that have shaped the universe since the moment of its birth. From the resonant frequencies of distant suns to the gravitational waves that ripple through space-time, these cosmic vibrations are the hidden threads connecting everything past, present, and future. By understanding them, we don't just unlock the mysteries of the stars, we uncover our own place in this grand, vibrating tapestry. So let's begin this journey together, stepping beyond the limits of what we can see and into the extraordinary world of what we can feel, the unseen music of the cosmos. The universe speaks in vibrations not with words, but through the very fabric of existence. From the smallest quantum particles to the vast swirl of galaxies, everything pulses with energy, moving in rhythms we're only beginning to decode. Think of a plucked guitar string. The tighter it's stretched, the higher the pitch. Stars operate on a similar principle. Their immense gravity and nuclear furnaces create pressures that make them vibrate like colossal tuning forks, emitting frequencies so precise they could be called musical notes. Astronomers have even detected stars oscillating in patterns that resemble the harmonies of a choir, their surfaces rippling like water disturbed by a stone. Some of the most compelling evidence comes from starquakes, violent tremors on a star's surface, captured by observatories like NASA's Chandra X-ray Observatory. These quakes send shockwaves through a star's interior, revealing hidden layers much like earthquakes help scientists map Earth's core. Then there are pulsars, the universe's natural metronomes. These rapidly spinning neutron stars beam radiation with such clockwork precision that their pulses can rival atomic clocks. Their rhythmic flashes act as cosmic lighthouses, helping astronomers navigate the darkest corners of space. But these vibrations do more than create celestial music. They're tools for uncovering the universe's deepest secrets. When a star's frequency shifts slightly, it can signal the presence of invisible forces, like dark matter's gravitational tug or the warping of space-time near a black hole. Scientists use these subtle changes like sonar, mapping the unseen structures that shape our cosmos. Even empty space isn't truly silent. Gravitational waves, ripples from colliding black holes echo across billions of light years, carrying stories of ancient cataclysms. This symphony of vibrations reshapes how we see the universe. Space isn't a static stage where events unfold. It's a dynamic, ever-shifting medium, alive with energy. Every ripple, every pulse is a conversation between matter and the forces that bind it, a dialogue written in frequencies older than time itself. And as we learn to listen, we're hearing the universe not just as it is, but as it sings itself into being. Long before telescopes or satellites, ancient cultures sensed the music of the cosmos. The Greeks imagined celestial bodies moving in perfect harmony, their orbits creating a symphony only the universe could hear. Pythagoras called it the music of the spheres, a theory that planets hummed as they traveled, their speeds and distances forming precise musical intervals. To him, the universe wasn't silent, it was a grand lyre, its strings plucked by the divine. His followers even claimed Saturn's deep, slow orbit rang like a bass note, while the moon's swift path sang in a high, clear tone. Though we now know space is airless, Pythagoras wasn't entirely wrong. Modern science reveals stars do vibrate at measurable frequencies, their pulses eerily reminiscent of his ancient vision. Half a world away, the Mayans built entire cities aligned to cosmic rhythms. Their pyramids doubled as resonant chambers, designed to amplify the frequencies of Venus and the Pleiades during sacred ceremonies. They believed stars weren't just lights but living entities, their vibrations influencing harvests, wars, even human destiny. Similarly, Vedic scholars in ancient India described Nada Brahma, the universe, as sound. Their sacred texts spoke of primordial vibrations giving rise to matter, a concept startlingly close to today's quantum theories. Indigenous astronomers across the Americas and Australia wove star songs into creation myths, teaching that celestial harmonies guided migrations, healed the sick, and connected the living to ancestral spirits. What's remarkable is how these scattered cultures, separated by oceans and millennia, all sensed the same truth: the cosmos pulses with unseen music. Today, we've swapped myth for math, but the essence remains. When astrophysicists study stellar oscillations or gravitational waves, they're hearing echoes of those ancient intuitions. The music of the spheres wasn't just poetry, it was humanity's first glimpse into vibrational cosmology. Now, with instruments like LIGO detecting spacetime's ripples or Kepler mapping starquakes, we're finally learning to translate that cosmic score. The universe hasn't changed, only our ability to listen. Light and sound may seem like separate languages of the universe, but in the cosmic symphony, they're intimately connected, just not in the way you might expect. Sound, as we know it, can't travel through the vacuum of space, yet stars and galaxies communicate through vibrations that scientists have learned to translate into something we can hear. Take sunlight, for example. Telescopes capture its electromagnetic waves invisible to our ears, but by shifting those frequencies downward, researchers can turn a star's radiation into a haunting hum. The result, a single note from the sun, sounds like the deep drone of a Tibetan singing bowl, resonating far below human hearing range. Then there's the Perseus Cluster's black hole, which astronomers discovered was singing in the lowest note ever detected, a B-flat 57 octaves below middle C. How superheated gas swirling around the black hole creates pressure waves that ripple through the surrounding cosmic medium, like ripples in a pond. While these waves aren't sound in the traditional sense, they vibrate at frequencies we can mathematically convert into audible tones. The effect is eerie, a cosmic bass note holding steady for billions of years, a lullaby for the abyss. This sonic alchemy isn't just poetic, it's revolutionary. By sonifying data from telescopes, scientists uncover hidden cosmic events. Gamma-ray bursts from colliding neutron stars become crashing cymbals. The magnetic pulses of distant pulsars morph into rhythmic clicks. These translations reveal patterns our eyes might miss, like how a musician hears dissonance in a chord. When NASA Chandra X-ray Observatory captured the sound of a supernova remnant, the vibrations exposed shockwaves rippling through debris. clues to how stars scatter the elements of life across space. What's astonishing is how these techniques blur the line between observation and experience. A galaxy's spin, translated into sound, becomes a rising melody. The solar wind's particles, rendered as static, whisper secrets about Earth's magnetic shield. Even silence speaks volumes. The hush of dark matter's gravitational pull hints at invisible mass bending the cosmos. By listening to light, we're not just studying the universe, we're feeling its pulse, one vibration at a time. Deep inside every star, there's a hidden rhythm, a heartbeat echoing through layers of superheated gas. These aren't just random tremors, they're precise vibrations, a celestial Morse code revealing secrets about the star's very soul. Scientists call this field Asteroseismology, the art of listening to stars. Just as earthquakes help geologists map Earth's core, starquakes let astronomers peer into the hearts of distant suns. Our own sun, for example, pulses with thousands of frequencies at once, its surface rising and falling in gentle waves like a breathing giant. These oscillations are born from turbulence in the star's interior, where nuclear fusion creates immense pressure, causing the entire structure to vibrate like a struck bell. The Kepler Space Telescope revolutionized this field by catching these subtle stellar quivers in over 500,000 stars. Imagine holding a microphone to the cosmos and hearing each star's unique hum, some steady as a drumbeat, others fluttering like a candle in the wind. These vibrations are so precise they can tell us a star's age within a few million years, its chemical composition, even whether it's hiding planets in orbit. A younger star might vibrate rapidly, full of youthful energy, while an older one groans with slower, deeper tones, hinting at its impending transformation into a red giant or white dwarf. But the most dramatic starquakes come from dying stars. When a massive star nears the end of its life, its core convulses, sending shock waves through its outer layers. These tremors can trigger supernova explosions so violent they outshine entire galaxies. Neutron stars, the dense remnants of such explosions, keep vibrating long after their death throes, spinning hundreds of times per second while ringing like cosmic gongs. By studying these vibrations, astronomers can predict which stars are on the verge of collapse or spot the birth cries of black holes. What's astonishing is how these stellar heartbeats mirror our own. Just as a doctor listens to a patient's pulse, scientists measure a star's vibrations to diagnose its health. A sudden shift in rhythm might reveal hidden companions, binary stars locked in a gravitational dance, or the first whispers of an impending stellar explosion. Every quake, every ripple is a verse in the star's life story, written in waves of light and pressure. And as we learn to decode them, we're not just studying distant suns, we're reading the autobiography of the universe itself. Among the most extraordinary performers in the cosmic symphony are Pulsars, neutron stars spinning so fast they could complete hundreds of rotations in the time it takes to blink. These dense stellar remnants, no larger than a city yet heavier than our sun, send out beams of radio waves that sweep across space like lighthouse signals. Each pulse arrives with such precision it rivals the most advanced atomic clocks on Earth, some ticking with millisecond accuracy over decades. It's as if the universe carved these objects to be perfect timekeepers, their rhythmic flashes so reliable that scientists once mistook them for artificial signals from distant civilizations. The secret lies in their incredible density. When a massive star collapses into a neutron star, its core compresses until protons and electrons merge into neutrons, packing the mass of a sun into a sphere just 12 miles wide. This forces the star to spin faster, the same way a figure skater accelerates when pulling their arms in. magnetic fields trillions of times stronger than Earth's focus radiation into narrow beams at the poles. As the star rotates, these beams sweep past our telescopes, creating the illusion of a pulsing light, an effect so regular you could set your watch by it. Pulsars didn't just become cosmic curiosities, they became proof. In the 1970s, astronomers discovered a binary pulsar orbiting another neutron star, its pulses subtly shifting as the pair spiraled closer. The timing matched Einstein's predictions perfectly, energy lost to gravitational waves bending spacetime itself. It was the first indirect evidence of these ripples, earning the researchers a Nobel Prize and cementing pulsars as laboratories for testing relativity. Now, these stellar metronomes might guide humanity's future among the stars. Spacecraft could one day use pulsar signals as interstellar GPS, triangulating positions by comparing arrival times of different pulsar beams. Some millisecond pulsars, spun up by stolen material from companion stars, are so stable their timing rivals Earth's best clocks, making them ideal reference points for navigating the vast dark between stars. Their vibrations, born from stellar death, could light the way to new worlds. Black holes may be the universe's most enigmatic singers, producing sounds so deep and ancient they defy human hearing. Take the Perseus Cluster's supermassive black hole, which astronomers discovered was emitting a B-flat 57 octaves below middle C, a note so low it took 34 million years to complete a single vibration. How does something so silent produce such profound music? The answer lies in the seething plasma around it. As gas spirals into the black hole's maw, it heats to millions of degrees, creating pressure waves that ripple through the surrounding cosmic medium like the slow-motion echoes of a gong. These waves aren't sound as we know it, they're vibrations in the fabric of space itself, detectable only when scientists shift their frequencies upward by quadrillions of times to render them audible. But black holes don't just hum, they crash. When two of these cosmic giants collide, they send shockwaves through space-time gravitational waves that LIGO, the Laser Interferometer Gravitational Wave Observatory, first detected in 2015. Imagine dropping two stones into a still pond. The ripples they create merge into chaotic patterns. Now replace the stones with black holes each 30 times the sun's mass, and the pond with the fabric of reality. The resulting waves, traveling at light speed, stretch and compress space itself as they pass, producing a chirp that lasts less than a second, but carries more energy than all the stars in the observable universe combined. LIGO instruments, sensitive enough to measure distortions 1,000 times smaller than a proton, captured this cosmic crescendo, proving Einstein's century-old prediction that spacetime could ripple like water. These dissonant harmonies are rewriting physics. Traditional telescopes see the universe in light, but gravitational waves let us hear its hidden movements, the mergers of neutron stars, the birth cries of black holes, even relics from the Big Bang's first seconds. Some theorize that primordial black holes formed in the universe's infancy might still be vibrating from that explosive dawn, their frequencies carrying clues about dimensions beyond our own. Others study ring-down phases, where a newly merged black hole settles into stability, vibrating like a struck bell until its surface becomes perfectly smooth, a phenomenon testing whether Einstein's equations hold true under extreme gravity. What's most astonishing is how these discoveries blur the line between destruction and creation. A black hole merger might seem like a violent end, but it's also a generative act, forging heavier black holes and scattering elements like gold and platinum across the cosmos. Their gravitational waves aren't just noise, they're the universe's way of conducting its own evolution, one collision at a time. And as we tune our instruments to listen deeper, we're not just observers of this symphony, we're audience members in a concert hall that stretches to the edge of time. Dark matter doesn't sing, it whispers, while stars and black holes send vibrations rippling through the cosmos. This mysterious substance, making up 85% of the universe's mass, remains stubbornly silent. It doesn't glow, reflect, or collide with ordinary matter the way atoms do. Yet scientists suspect it might hum in frequencies so faint, our detectors haven't been sensitive enough to catch them. Imagine standing in a room where someone's playing a note just beyond the edge of hearing. You can't quite grasp it, but you feel its presence in the air. That's the puzzle of dark matter, an invisible orchestra shaping galaxies from the shadows, its instruments tuned to a scale we're only beginning to imagine. The hunt for these elusive vibrations hinges on a radical idea that dark matter particles, though nearly intangible, might still interact weakly with ordinary matter. Some theories suggest they could cause ultra-subtle tremors in specially designed crystals or supercooled chambers, like a single snowflake landing on a drumhead. Experiments like Super Cryogenic Dark Matter Search and LUX Zeppelin are built to listen for these whispers, using materials so sensitive they could detect the energy of a flying mosquito. Spread across an entire year, if dark matter particles pass through, they might leave behind vibrations 1 billion times smaller than an atom's width. A signature scientists could amplify into a detectable signal. What makes this search so thrilling is the scale of the mystery. Galaxies spin faster than their visible mass should allow, as if gripped by unseen hands. Gravitational lensing bends light around empty patches of space, revealing the ghostly pull of something we can't see. Dark matter's gravitational fingerprints are everywhere, yet its nature remains one of cosmology's greatest riddles. If future detectors catch its vibrations, it wouldn't just solve a puzzle, it would rewrite our understanding of reality. We might discover that dark matter isn't a single note but a chorus of particles, each with its own frequency, weaving the hidden scaffolding of the cosmos. The irony is poetic. For centuries, we've relied on light to unveil the universe's secrets. Now, we're learning to listen instead to the quietest hums, the faintest tremors, the vibrations that might finally give voice to the darkness. And when we do, we won't just hear dark matter, we'll hear the universe speaking in a language older than stars. If you could rewind the universe back to its infancy, just 380,000 years after the Big Bang, you wouldn't find stars or galaxies, only a swirling sea of particles so hot and dense, light couldn't travel more than an inch before being swallowed again. Then, in a cosmic flash, everything changed. Space cooled enough for atoms to form, releasing light to travel freely for the first time. That ancient glow still surrounds us today, faded to a whisper after 13.8 billion years, the cosmic microwave background. But this isn't just light, it's a frozen echo of the universe's first vibrations, a snapshot of sound waves rippling through the newborn cosmos. These primordial sound waves were born from the universe's earliest chaos. Imagine dropping a stone into a pond, except here, the pond is the fabric of space-time, and the stone is the explosive energy of creation itself. As matter and radiation pushed against each other, they created pressure waves that traveled at half the speed of light, compressing gas into dense regions that would one day become galaxies. The cosmic microwave background captures these waves at the moment they were frozen in time, like a phonograph record pressed into the sky. Tiny fluctuations in temperature, hotter spots where matter was compressed, cooler spots where it was rarefied form a pattern scientists call the Barrian acoustic oscillations, a blueprint for how the universe organized itself. What's astonishing is how precise this fossilized music is. By measuring these temperature variations, astronomers can reconstruct the universe's original, Note, a bass tone so deep it would take tens of thousands of years to cycle once. The European Space Agency's Planck satellite mapped these fluctuations with such detail. It revealed the cosmos is tuned to a frequency of about 100 times lower than the deepest sound humans can hear. This hum wasn't random noise. It carried precise information about the universe's composition, helping confirm the existence of dark matter and dark energy. But the most profound revelation lies in the patterns themselves. Those ripples weren't just random noise, they were the seeds of everything. The slightly denser regions pulled in more matter through gravity, growing over billions of years into the galaxies and cosmic webs we see today. In essence, the cosmic microwave background is a musical score written in heat and light, its harmonies predicting where stars would ignite and where vast voids would stretch. We're not just observing the past, we're hearing the universe's first draft, a composition that shaped every structure from galaxy clusters to the atoms in our bodies. And as we listen closer, we're uncovering new verses and anisotropies that hint at physics beyond our current understanding, whispers of a time before time. Deep in the swirling chaos of a young solar system, something extraordinary happens. Dust begins to dance, not randomly, but in perfect sync with the vibrations of its parent star, as if following an invisible conductor's baton. These protoplanetary disks, vast rings of gas and debris surrounding newborn stars, aren't just passive nurseries for planets, they're resonant chambers where cosmic frequencies decide which particles stick together and which drift apart. Picture a violin bow drawn across a dusty table. Certain grains jump and cluster where the vibrations peak, while others scatter. On a stellar scale, this same principle guides the birth of worlds, with starry hums nudging specks of dust into the first whispers of planets. Scientists call this process acoustic resonance, and it's far more precise than mere chance. When a star's vibrations ripple through its surrounding disk, they create zones of high and low pressure regions where dust particles experience rhythmic tugs, coaxing them into synchronized orbits. Over millennia, these particles harmonize, colliding gently rather than destructively, growing from microscopic motes into pebbles, then boulders, and eventually the building blocks of planets. The ALMA telescope has captured stunning images of these resonant gaps in disks, revealing concentric rings where fledgling planets sweep up debris in time with their star's pulse. It's a celestial waltz with gravity and vibration as partners. Earth itself may carry echoes of this cosmic tuning. Our planet resonates at a frequency of around 7.83 Hz, the Schumann resonance, a hum generated by lightning strikes exciting the cavity between Earth's surface and the ionosphere. But here's the eerie part. This frequency overlaps with the alpha rhythms of the human brain, the electrical pulses that arise when we're relaxed or meditative. Coincidence? Some researchers speculate that after billions of years immersed in Earth's natural frequency, life may have evolved to resonate with it, just as ancient dust tuned itself to stellar vibrations. The implications are profound. If resonance sculpted our solar system, could it also shape life's blueprint? From the spin of galaxies to the firing of our neurons, vibration seems to be a universal language, one that connects the birth of planets to the rhythms of biology. We're not just observers of this symphony, we're instruments within it, vibrating in ways we're only beginning to understand. Some people swear they've heard the northern lights, a faint crackling or humming as green ribbons shimmer across the Arctic sky. Scientists dismiss it as folklore, since sound can't travel through the near vacuum where auroras form. Yet recent research suggests these witnesses might not be imagining things. When solar particles collide with Earth's magnetic field, they can generate ultra-low frequency radio waves imperceptible to our ears that interact with objects on the ground. A hiker's backpack frame, a wire fence, even dry snow might vibrate subtly, translating those cosmic signals into whispers just within human hearing range. It's as if the planet itself becomes a translator, turning the sun's fury into something almost musical. This idea that humans might sense cosmic vibrations goes beyond auroras. Studies in neuroacoustics reveal our brains respond to rhythmic patterns mirroring natural frequencies, from ocean waves to planetary orbits. When volunteers listen to recordings of solar wind data converted into sound, their brainwaves often synchronize with the rhythms, entering states of calm focus. Ancient cultures seem to intuit this connection. Tibetan monks chant at frequencies that resonate with Earth's Schumann resonance, while Aboriginal songlines map landscapes through melodies said to echo the stars' movements. Even modern meditation practices use binaural beats, sound waves tuned to frequencies believed to align with cosmic vibrations, to induce deep relaxation or heightened awareness. Science is now probing these intersections between perception and physics. The HeartMath Institute has documented how human heart rhythms shift during solar storms, as if our bodies tune into electromagnetic changes in the environment. Meanwhile, CERN researchers explore whether consciousness itself might interact with quantum fields, the same fields that vibrate through all matter. It's a frontier where spirituality and particle physics collide, raising provocative questions. Could our brains be biological antennas, subtly attuned to the universe's hum? When a composer like Holst writes The Planets, is he channeling something deeper than metaphor? The most compelling evidence lies in our cells. Every atom in our bodies, the iron in our blood, the calcium in our bones, was forged in the hearts of stars, vibrating with the same frequencies that now pulse through distant nebulae. We're not just observers of the cosmic symphony, we're made from its notes. Whether through science or song, humans have always sought to hear the music of the spheres. Perhaps the answer isn't in our ears, but in the quiet resonance between the universe's oldest vibrations and the rhythm of being alive. The sun doesn't just shine, it sings. Every 11 years, our star reaches a crescendo of activity, its surface erupting with sunspots and solar flares in a cycle as reliable as a metronome. These aren't just visual spectacles. They're the surface ripples of deeper vibrations within the sun's core, where fusion-generated pressure waves rise like bubbles in a boiling pot, eventually breaking through to create magnetic storms. When these storms reach Earth, they don't just light up polar skies, they rewrite the rules of our climate and technology, proving we're all dancing to a solar rhythm few of us ever hear. Take the Maunder minimum, a 70-year period in the 17th century when sunspots nearly vanished. Temperatures in Europe plummeted so drastically that the Thames River froze solid enough to host winter festivals, a climatic shift now linked to the sun's muted vibrations during that era. Modern satellites have caught the mechanism in action. When solar activity dips, ultraviolet radiation dwindles, weakening Earth's stratospheric winds. This disruption trickles down to surface weather patterns, steering jet streams off course and triggering prolonged droughts or unseasonal rains. Conversely, during solar maximums, heightened ultraviolet output can warm the upper atmosphere by several degrees, altering pressure systems that guide hurricanes and monsoons. But the sun's influence isn't limited to gradual shifts. Coronal mass ejections, violent eruptions of charged particles, can slam into Earth's magnetic field at 1,000,000 miles per hour, inducing electrical currents in power grids strong enough to melt transformers. In 1989, a geomagnetic storm triggered by such an event blacked out Quebec for 9 hours, leaving millions in the dark. Satellite operators dread these solar tantrums, as heightened radiation can fry sensitive electronics in orbit. GPS signals distort, radio communications fizzle, and even airline passengers near polar routes risk exposure to elevated radiation levels. What's fascinating is how these disruptions mirror musical principles. Just as a loud note can overwhelm an acoustic space, solar outbursts overload Earth's electromagnetic resonance chamber. Scientists measure these interactions through Schumann resonances, standing waves in the atmosphere created by lightning, which solar activity can amplify or dampen like a cosmic volume knob. During severe storms, these frequencies spike, creating feedback loops that may influence animal migration and human circadian rhythms. Birds navigating by magnetic fields grow disoriented. Whales beach themselves during solar disturbances. Even the human nervous system shows subtle shifts in electrical activity. The deeper implication is one of cosmic entanglement. The same vibrations that govern the sun's interior also conduct Earth's climate symphony, with our atmosphere acting as both instrument and audience. Satellites like NAS, a solar dynamics observatory, now track these connections in real time, converting solar oscillations into audible tones that reveal patterns resembling minimalist music, repetitive yet subtly evolving. As we decode these solar harmonies, we're not just predicting space weather, we're learning to listen to the star that gives us life, one resonant vibration at a time. What if the universe has been broadcasting messages all along, not in words or pictures, but in vibrations? For decades, humanity has beamed radio signals into space, hoping to catch the attention of extraterrestrial civilizations. But there's another, far older language woven into the fabric of reality itself, the rhythmic pulses of neutron stars, the resonant hum of black holes, the gravitational waves rippling across space-time. These cosmic vibrations might hold the key to interstellar communication, not because they're deliberate signals, but because they're universal. Every advanced civilization, no matter how alien, would share one common experience: the ability to detect the universe's vibrational symphony. Consider pulsars. These spinning neutron stars emit beams of radiation with such precise regularity. They could serve as natural lighthouses for galactic navigation. Scientists have proposed encoding messages in their timing variations, tiny, deliberate delays or accelerations in their pulses that artificial intelligence could distinguish from natural irregularities. Imagine a sequence of pulses spelling out prime numbers or mathematical constants, a cosmic Morse code etched into the spin of a dead star. The Arecibo message, sent in 1974, used radio waves, but future dispatches might manipulate pulsar beams instead, turning these celestial metronomes into interstellar telegraph. Gravitational waves offer an even more radical medium. Unlike light, which scatters or dims over distance, these ripples in space-time travel unimpeded, passing through stars and dust without distortion. A sufficiently advanced civilization could theoretically imprint information onto gravitational waves, perhaps by colliding black holes in precise sequences, creating chirps that form a binary code. The LIGO Observatory has already detected these waves. What if we someday find patterns in them that don't match natural astrophysical events? Some researchers speculate that the universe's first gravitational wave message might not come as a deliberate transmission, but as an accidental byproduct of alien engineering, like the hum of a distant machine vibrating through the cosmos. Yet the most profound idea isn't about crafting new messages, it's about recognizing the ones already surrounding us. The universe is full of resonant frequencies that could act as universal reference points. Hydrogen, the most abundant element in the cosmos, emits radio waves at a wavelength of 21 centimeters, a natural hello frequency that any civilization studying astronomy would discover. Similarly, the cosmic microwave backgrounds harmonics, or the Schumann resonances of exoplanets, might serve as shared cultural touchstones, allowing species separated by light years to find common ground in the physics of vibration. This shifts how we think about contact. Instead of waiting for aliens to build radio transmitters, we might search for anomalies in the cosmic symphony, a pulsar skipping a beat, a gravitational wave with artificial structure, even an exoplanet's atmosphere vibrating in resonant patterns that defy natural explanations. The universe isn't silent. It's a vast, vibrating network where every star, every black hole, every particle is both instrument and listener. If we learn to speak its language, we might discover we're not just reaching into the darkness, we're joining a conversation that began billions of years before Earth formed. Look closely at a sunflower's spirals or the curve of a nautilus shell, and you'll notice a hidden pattern, the Fibonacci sequence, where each number is the sum of the two before it. This mathematical marvel doesn't just decorate Earth's flora, it's woven into the fabric of the cosmos itself. Spiral galaxies like the Whirlpool or the Milky Way's own arms unfurl in logarithmic spirals that mirror the golden ratio, a proportion derived from Fibonacci numbers. The tighter the spiral, the more it approximates this divine ratio, 1.618 to 1, a harmony so precise it feels intentional. Even the distribution of stars in clusters like the Pleiades often follows Fibonacci spacing, as if the universe has a favorite blueprint. But why does this pattern recur across scales? The answer lies in efficiency. In nature, growth often follows the path of least resistance, and Fibonacci spirals allow for maximal packing, whether it's seeds in a sunflower or stars in a galaxy. When a rotating cloud of gas collapses under gravity, it naturally spins faster, flattening into a disk where material clumps along these optimal curves. Planetary orbits, too, hint at this resonance. The time it takes Venus to orbit the Sun forms a near-perfect golden ratio with Earth's year. 8 Venusian years equal almost exactly 5 Earth years, tracing a 5-pointed star in our sky. The connection deepens when we consider vibration. Musical intervals that sound harmonious like a perfect fifth correspond to Fibonacci ratios. A violin string divided at the golden point produces the most pleasing tone. Similarly, spiral galaxies sing in gravitational harmonics, their arms vibrating with density waves that compress gas into new stars. Even hurricanes, those terrestrial tempests, spin in Fibonacci spirals, their winds obeying the same fluid dynamics as interstellar clouds. This isn't mere coincidence, it's a universal language of resonance. From the microscopic chambers of a seashell to the vast whirl of a quasar, the same patterns emerge, a testament to the deep bond between mathematics, music, and the cosmos. The universe doesn't just compute, it composes, and in its grand symphony, the golden ratio is the recurring refrain. At the smallest scales of reality, the universe doesn't just hum, it shivers. Quantum fluctuations, those fleeting bursts of energy that pop in and out of existence, might be more than microscopic curiosities. They could be the seeds of entire universes, each with its own vibrational fingerprint. Imagine a frothing ocean where every bubble isn't just empty space but a self-contained cosmos, born from a quantum tremor and tuned to a unique frequency. This isn't science fiction, it's a leading edge of theoretical physics known as the Multiverse hypothesis. And if it's true, our universe's symphony might be just one movement in an infinite cosmic concerto. The math behind this idea hinges on inflation, the explosive expansion of space-time in the universe's first moments. According to some models, quantum vibrations during inflation could have stretched into vast regions, each crystallizing into a separate universe with distinct physical laws. Some might vibrate at higher energies, their particles buzzing like hyperactive violin strings. Others could resonate at lower frequencies, where gravity dominates and stars form in slow, ponderous rhythms. The wildest possibility that these alternate realities aren't just out there, they're brushing against our own. Certain anomalies in the cosmic microwave background, like the infamous cold spot, have sparked speculation that we might be detecting gravitational echoes from a neighboring universe's birth pangs. String theory takes this harmony even deeper. If the universe's fundamental building blocks aren't particles but vibrating strings, then every particle, every force, is just a different note played on those strings. The catch: these strings don't vibrate in the 3 dimensions we know. They dance through 10 or 11 dimensions, most curled up so tiny we'll never perceive them directly. Yet their shapes, their geometry determine how strings vibrate, which in turn sets the laws of physics for each universe. A slight twist in these hidden dimensions could mean the difference between a cosmos where light travels 1,000,000 times faster or one where atoms never form. The implications are staggering. If every possible vibration corresponds to a possible universe, then somewhere out there, a reality exists where stars sing in perfect fourths instead of fifths, where black holes emit chirps rather than drones, even one where the very concept of music is unknown. We may never visit these alternate worlds, but their vibrations could leave traces in our own. Some physicists search for gravitational lensing patterns that might betray a neighboring universe's pull, while others analyze quantum entanglement for signs of interaction with parallel realities. What's most poetic is how this bridges the ancient and the cutting edge. The Hindu concept of Nada Brahma, the universe as sound, finds eerie resonance in string theory's vibrating filaments. Indigenous creation myths describing worlds layered like musical notes suddenly don't seem so metaphorical. Whether through math or myth, humanity has always sensed that reality is more than what we see, it's what we hear, or rather, what we're only beginning to listen for. And if the multiverse is real, then every vibration, from the quantum jitter to the galactic spin, is a verse in a song without end. NASA has transformed the way we experience the cosmos by letting us listen to it. Through their groundbreaking sonification projects, raw astronomical data, images, radiation levels, even particle collisions, becomes immersive soundscapes, revealing patterns our eyes might miss. Take the haunting melody of the Milky Way's core, where X-ray, infrared, and visible light data from telescopes like Chandra and Hubble were mapped to different instruments. Stars twinkle as chimes, interstellar dust hums like a cello, and the supermassive black hole at the center resonates as a deep, pulsing bass. The result isn't just artistic, it's a revelation. Blind astronomers can now hear galactic structures, while sighted researchers detect asymmetries in spiral arms or gas densities through shifts in timbre and volume. These cosmic compositions aren't arbitrary. Brightness dictates pitch. Brighter stars sing higher notes, while distance from the image center controls stereo panning, creating a 3D effect. Meteor showers, typically silent in reality, become staccato percussion when scientists translate each meteoroid's speed and size into rhythmic clicks and pops. Even Saturn's rings have a voice. Data from the Cassini mission was converted into shimmering tones that change as the spacecraft dipped between the rings, exposing variations in ice density. But the most profound impact might be emotional. When the pillars of creation, those towering columns of gas in the Eagle Nebula, were sonified, their ethereal drones evoked something primal, like the universe breathing. Similarly, the sound of a black hole's pressure waves in the Perseus cluster, initially dismissed as spooky noise, went viral for its uncanny resemblance to a horror movie score. Yet these sounds aren't embellished. They're mathematical translations, proving that beauty emerges naturally from cosmic physics. By turning light into sound, NASA isn't just making space accessible. They're reminding us that the universe communicates in frequencies beyond our senses. A supernova's aftermath might look like a static image, but when heard, its shockwaves ripple outward in crescendos, telling the story of stellar death in a language that bypasses the eyes and speaks directly to the soul. This isn't just science, it's the cosmos singing its autobiography, one vibration at a time. Long before telescopes or spectrometers, ancient cultures recorded sky-born omens that shook civilizations to their core, blaring trumpets from heaven, fiery dragons streaking across the night, even the sound of stars falling like shattering glass. The Book of Revelation describes 7 angels sounding trumpets that bring hail, fire, and a great star falling to poison the waters. Norse mythology speaks of the Gjallarhorn, whose blast would herald Ragnarök, the end of the world. For centuries, these accounts were dismissed as mere allegory, but modern astronomy reveals an eerie possibility. These myths might encode real cosmic cataclysms, their terrifying sounds born from vibrations we can now measure. Take gamma ray bursts, the most violent explosion since the Big Bang. When a massive star collapses into a black hole, it can unleash a jet of radiation so powerful it outshines an entire galaxy for seconds. If one occurred within a few thousand light-years of Earth, the initial flash would sear the ozone layer, followed by a sonic boom of high-energy particles vibrating our atmosphere. Ancient observers wouldn't have seen the burst itself, but its aftermath might have manifested as deafening cracks, eerie hums, or even resonant tones as charged particles interacted with Earth's magnetic field. The trumpet, described in multiple cultures, could have been the ionosphere itself vibrating like a colossal speaker, translating cosmic violence into audible terror. Then there's the 1170 BC event. Tree rings from that era show a sudden spike in radioactive carbon-14, while Irish annals describe blood-red skies and dreadful noises. Scientists now suspect a nearby supernova or solar superflare events that would have bathed Earth in radiation while generating ultra-low-frequency infrasound. At certain pitches, infrasound can induce primal fear, vibrating internal organs and creating sensations of awe or doom. No wonder cultures from the Aztecs to the Babylonians interpreted these vibrations as divine warnings. The Tunguska explosion of 1908 offers a modern parallel. When a meteorite detonated over Siberia, the blast flattened 800 square miles of forest, but witnesses hundreds of miles away reported something stranger, a series of rolling booms that lasted for hours. These weren't just shockwaves, they were atmospheric oscillations, the sky ringing like a bell struck by a cosmic hammer. Similar events in antiquity, like the suspected asteroid impact that sparked the Younger Dryas cooling 12,000 years ago, could have generated weeks of harmonic reverberations, fueling legends of celestial battles or gods at war. What's fascinating is how consistently these accounts describe not just light, but sound, a detail science can now explain. When a comet's plasma tail interacts with solar wind, it can generate electromagnetic waves at audio frequencies. Converted to sound, these waves produce unearthly hisses or chirps, perhaps inspiring the serpent's breath in Chinese comet lore. Even auroras, now known to create very low-frequency radio emissions, might explain the singing skies of Sami and Inuit traditions, where the northern lights were said to whisper or clap. These myths aren't just stories, they're humanity's first attempts at astrophysics, using the language of vibration to explain the inexplicable. Today, we've swapped omens for observatories, but the awe remains. When LIGO detected gravitational waves from colliding black holes, the event was nicknamed the Chirp, a soundbite from the abyss that, had it been stronger, might have vibrated the bones of every creature on Earth. The universe hasn't changed, only our ability to listen has. And as we decode these ancient sky songs, we're rediscovering a truth written in starlight and shockwaves. The cosmos doesn't just show us its power, it lets us hear it. The next revolution in cosmic listening is already on the horizon, and it promises to tune our ears to frequencies we've never before been able to detect. Imagine a trio of spacecraft floating 1,000,000 miles apart, connected by lasers so precise they could measure the width of an atom shifting across that vast distance. This isn't science fiction, it's LISA, the Laser Interferometer Space Antenna, a mission set to launch in the 2030s that will open a new window into the universe's hidden soundtrack. While ground-based observatories like LIGO have given us fleeting snapshots of black hole collisions, LISA will listen for the deep, rumbling mergers of supermassive black holes, events so colossal they warp spacetime itself, sending vibrations that ripple across millions of light years. What makes LISA so extraordinary is its sensitivity to low-frequency gravitational waves, the kind produced by black holes billions of times heavier than our Sun. These cosmic titans don't collide with a bang, but with a slow, cosmic groan, their gravitational waves oscillating over years rather than seconds. Picture two whales singing to each other across an ocean of spacetime, their calls too deep for human ears, yet carrying unimaginable power. LISA Laser Network will catch these ultra-low frequencies, revealing how supermassive black holes dance toward merger, how they shape the galaxies around them, and perhaps even echoes from the universe's birth. But LISA is just the beginning. The Einstein Telescope, a proposed underground observatory, aims to detect gravitational waves with 10 times LIGO precision, hunting for the faint whispers of primordial black holes or cosmic strings, hypothetical defects in spacetime left over from the Big Bang. Meanwhile, pulsar timing arrays are turning entire galaxies into gravitational wave detectors by monitoring how these spinning stars' rhythms are perturbed as waves pass through them. It's like using 1,000 metronomes scattered across the Milky Way to sense the universe's subtle tremors. The most tantalizing possibility, these tools might finally hear the stochastic background, the faint hum of countless gravitational waves overlapping from every black hole merger in cosmic history. This would be the ultimate soundtrack of the universe, a chorus of collisions stretching back to the first stars. Some theories suggest it could even carry traces of inflation's quantum vibrations, the primordial seeds that grew into galaxies. What's clear is this: we're not just building better telescopes, we're composing a new kind of astronomy, one where vibration replaces light as our primary lens. Soon we'll listen to the universe not in snapshots, but in symphonies, each note a black hole's birth cry, each chord a galaxy's formation song. And as these technologies come online, we won't just observe the cosmos. We'll finally hear it breathe. You don't need $1 million observatory to tune into the universe's symphony. Your backyard and a smartphone might be enough. Radio telescopes have long transformed celestial signals into audible sound, but today, free apps like Radio Garden or NASA's own space sounds let anyone eavesdrop on satellites, pulsars, and even the cosmic microwave background with just a few taps. Start by pointing your phone's radio telescope app toward Jupiter. Its raging magnetic field generates eerie whistles and pops as it interacts with its moon Eo's volcanic eruptions, sounding like an otherworldly storm. For a deeper dive, online platforms like the University of Iowa's Radio Jove project sell affordable kits to build your own radio telescope. These homemade devices can pick up solar bursts, explosions on the sun's surface that crackle like static but carry enough energy to disrupt Earth's communications. Time your observations during a solar maximum, and you might catch what scientists call a Type 3 radio burst, a high-pitched scream of electrons racing along magnetic field lines. If DIY hardware isn't your style, websites like WebSDR connect users to live feeds from professional radio telescopes worldwide. Tune into the Arecibo Observatory's archives even post-collapse. Its data remains priceless, and you'll hear the haunting Doppler shifts of passing asteroids or the rhythmic beeps of the ISS's telemetry signals. Amateur astronomers have even discovered new pulsars this way, their telltale pulses standing out like Morse code against the cosmic noise. The magic lies in the translation process. Space doesn't transmit sound waves, but electromagnetic vibrations, radio waves, X-rays, gamma rays, get converted into audio frequencies we can hear. Apps like Astrosonic map brightness to pitch, so when a meteor burns up in Earth's atmosphere, it doesn't just streak silently, it sings a brief, fiery note. Some enthusiasts take this further, using MIDI controllers to turn real-time satellite data into ambient music, blending science with art. What's thrilling is how accessible this has become. Schools in Norway track the Northern Lights radio emissions using simple wire antennas, while a teenager in Australia once decoded the faint heartbeat of a dying star using public data from the Parkes telescope. The universe's vibrations aren't just for experts, they're a shared experience, waiting for anyone curious enough to listen. And when you hear that first pulsar's steady beat through your headphones, you're not just observing the cosmos, you're joining a conversation 13.8 billion years in the making. What happens when humanity gains the power to remix the cosmos? The idea of manipulating stellar vibrations, tweaking a star's frequency to extend its life, or damping a black hole's resonant hum to stabilize nearby planets sounds like science fiction. Yet with advances like directed energy systems and quantum-scale engineering, these possibilities inch toward reality. Imagine a future where we could tune a dying star like a piano, adjusting its oscillations to delay a supernova. Or picture satellites emitting gravitational waves to steer asteroids away from Earth, using space-time itself as a cosmic bumper. The technology remains speculative, but the ethical dilemmas are already here. If we can alter the universe's vibrations, does that mean we should? The risks are as vast as space itself. Stars aren't isolated instruments, they're part of a galactic orchestra. Changing one frequency could ripple across light years, disrupting delicate gravitational balances. A pulsar's rhythmic beams might guide interstellar travelers, but adjusting its spin could throw off navigation for entire civilizations. Even subtle interventions like using resonance to nudge a protoplanetary disk into forming more Earth-like worlds might unintentionally sterilize emerging life elsewhere in the system. History warns us, when humans introduce foreign frequencies into ecosystems, from sonar disorienting whales to light pollution obscuring celestial navigation, the consequences often surprise us. Scaling this up to stellar engineering invites unknown chaos, yet the potential rewards glitter just as brightly. Suppose we could stabilize a hyperactive young star's vibrations to prevent lethal solar flares, or slow a black hole's merger to study spacetime's fabric in slow motion. Such control could make hostile regions of the galaxy habitable, even preserving civilizations orbiting unstable stars. Some theorists propose acoustic terraforming, using resonant frequencies to sculpt nebulae into optimal star-forming regions, essentially composing new stellar nurseries. The moral argument here echoes medicine's Hippocratic oath. If we have the power to heal cosmic bodies, withholding that knowledge could be its own ethical failure. The debate splits along philosophical lines. Preservationists argue the universe's vibrations are a sacred text, written over billions of years. Our role is to listen, not edit. Interventionists counter that intelligence exists to shape chaos into order, just as life transformed Earth's atmosphere. Indigenous cosmologies add nuance. Many traditions view celestial harmonies as living dialogues, where reciprocity matters more than control. Meanwhile, legal scholars grapple with jurisdiction who decides the correct frequency of a star, a planet orbiting it, a distant species relying on its pulses for cultural rituals. Perhaps the answer lies in humility. Before we play Universe's DJ, we might first learn its language, studying how vibrations connect ecosystems across scales, from quantum fields to galaxy clusters. Projects like messaging extraterrestrial intelligence already face criticism for broadcasting Earth signals into space uninvited. Manipulating stellar frequencies would be exponentially louder, a shout across the cosmic choir. Until we understand the full score, the safest course might be to keep listening, to hear not just the notes but the silence between them. After all, the most beautiful symphonies leave room for every instrument to breathe. Black holes have long been thought of as cosmic shredders. Once something crosses their event horizon, it's gone forever, crushed into oblivion. But what if that's not the whole story? Enter one of the most perplexing puzzles in modern physics, the black hole information paradox. At its heart is a simple question: when a black hole devours a star, a planet, or even an entire library's worth of information, does that data vanish from the universe entirely? Quantum mechanics says no, information can't be destroyed. Yet general relativity insists that whatever falls into a black hole stays there. So where does the truth lie? The answer might be written in vibrations, specifically the faint quantum hum of Hawking radiation. Stephen Hawking's revolutionary idea was that black holes aren't completely black. They emit a slow trickle of particles now known as Hawking radiation, leaking energy over unimaginable timescales until they eventually evaporate. Here's where things get fascinating. This radiation isn't random noise. It's theorized to carry subtle imprints of everything the black hole ever consumed, like grooves on a cosmic vinyl record. Imagine a black hole swallowing a star. As the star's matter is stretched and compressed, its quantum information gets scrambled into chaotic vibrations at the event horizon. But according to some models, those vibrations leave faint echoes in the Hawking radiation, encoding the star's song in the escaping particles. The universe, it seems, might keep backup tapes after all. This idea turns black holes into unexpected archivists. Just as sound waves can reconstruct a shattered wine glass if you catch all their frequencies, physicists like Leonard Susskind propose that Hawking radiation's vibrational patterns could, in theory, be reverse engineered to reconstruct what fell in. It's as if the black hole's surface acts like a quantum hard drive, vibrating in ways that preserve data even as the object itself disappears. The math suggests these vibrations follow holographic principles, where information isn't lost but projected onto a lower dimensional boundary, like a 3D movie encoded on a 2D screen. Yet mysteries remain. If information escapes via Hawking radiation, how does it avoid being hopelessly scrambled? Some theories suggest black holes have soft hair, extra quantum fields at their edges that vibrate gently, storing data like grooves in a record. Others argue that space-time itself might vibrate in hidden dimensions, preserving information in ways we can't yet detect. The debate is far from settled, but what's clear is this: the universe seems to abhor forgetting. Whether through vibrations, radiation, or some deeper quantum symphony, the cosmos appears wired to keep every note of its history, even in the face of oblivion. This isn't just theoretical gymnastics, it's a window into the nature of reality itself. If black holes don't destroy information but transform it, then time, space, and even causality might be more flexible than we thought. Future gravitational wave detectors could hunt for vibrational fingerprints in merging black holes, searching for clues in the ripples they leave behind. One day, we might even decode the Hawking radiation from a dying black hole, playing back the universe's lost melodies like a cosmic mixtape recovered from the abyss. Until then, the paradox reminds us that in a universe built on vibrations, nothing truly disappears, it just changes key. Time might feel like an unchanging constant, ticking forward with mechanical precision. But what if it's more like a song, its rhythm dictated by the vibrations of the universe itself? Think of the world's most accurate timekeepers, atomic clocks. They don't measure seconds with gears or pendulums, but by counting the oscillations of cesium atoms over 9 billion vibrations per second. These atoms don't just keep time, they are time. They're steady pulses defining the very fabric of our schedules, our technologies, even our understanding of reality. Yet this precision isn't unique to Earth. Out in the cosmos, pulsars spin with such metronomic regularity that their beams arrive with timing rivaling atomic clocks. Their rhythms so reliable they've been called the universe's natural chronometers. The eerie similarity between these two timekeepers, one atomic, one cosmic, hints at something profound. Time might not be a separate dimension at all, but a symphony of vibrations woven into the fabric of existence. Consider how time behaves under extreme conditions. Near a black hole's event horizon, where gravity warps spacetime, clocks slow dramatically, a phenomenon called time dilation. But this isn't just a distortion of some abstract clock. It's a change in the vibrational rates of everything within that space. Atoms jitter slower, light redshifts to longer wavelengths, even the decay of particles stretches out. Time doesn't just slow, it resonates differently, as if the universe itself is tuning the frequency of reality. String theory takes this further, suggesting that time could emerge from the vibrations of infinitesimal strings, their oscillations creating not just particles but the very flow of moments. If true, then the past, present, and future might be less like points on a line and more like notes in a chord, vibrating together in a cosmic harmony. The implications ripple through physics. If time is vibrational, could we manipulate it by altering those frequencies? Experiments with supercooled atoms in Bose-Einstein condensates show that under certain conditions, quantum vibrations can appear to reverse, creating localized pockets where entropy decreases, a hint that time's arrow might not be absolute. Even our perception of time's flow might be tied to resonance. The human brain processes information in rhythmic waves, with neural oscillations governing how we experience duration. When those rhythms are disrupted by trauma, drugs, or even deep meditation, time can feel like it speeds up, slows down, or stops altogether. This isn't just subjective. It suggests our brains might be sinking to a deeper, universal tempo. Perhaps the most mind-bending possibility is that time isn't fundamental at all, but an emergent property, a collective hum rising from countless quantum vibrations. Just as temperature emerges from the motion of molecules, time could be the universe's way of making sense of underlying oscillations. Pulsars, atomic clocks, even our own circadian rhythms would then be instruments in this grand orchestra, each playing its part in the cosmic score. If we ever learn to hear the full melody, we might discover that time isn't slipping away, it's singing itself into existence, one vibration at a time. The haunting organ chords of Interstellar don't just set the mood, they are the mood. When Hans Zimmer composed the film's score, he didn't just write music about space, he channeled its vibrations into sound. The deep, resonant pulses mirror the time-warping effect of a black hole's gravity. while the eerie harmonics echo the quantum fluctuations of a fifth-dimensional library. It's no accident that the soundtrack feels less like a backdrop and more like a character, as if the universe itself is singing its secrets. Zimmer collaborated with physicist Kip Thorne to translate Einstein's equations into musical notes, bending sound waves the way space-time bends light. The result, a score that doesn't just accompany the visuals. It becomes the fabric of the cosmos, vibrating at frequencies that feel ancient and alien. This interplay between cosmic vibrations and creativity isn't new. Pink Floyd's Dark Side of the Moon famously syncs with The Wizard of Oz, but the album's true muse was the Apollo missions. The heartbeat opening Speak to Me mimics the rhythmic pulses of a liftoff countdown, while On the Run's oscillating synths evoke the disorienting hum of deep space. The band didn't just sing about the moon, they sonified the isolation and awe of leaving Earth's atmosphere. Even the album's prism cover art mirrors how light splits into frequencies, a nod to the universe's hidden spectrum. Science fiction has long borrowed this vibrational language. Star Trek's warp core hum isn't just futuristic ambience, it's a sonic metaphor for bending space-time. 2001, A Space Odyssey opens with Ligeti's Requiem, a chorus of voices clashing in dissonant harmonies, a soundscape so unsettling it embodies the vast, unknowable cosmos. Even Doctor Who's TARDIS wheezes like a dying star, its groans pulled from a 1950s oscillator recording. These aren't random choices, they're artistic translations of cosmic resonance, turning astrophysics into emotional shorthand. But the influence flows both ways. When Voyager 1 left the solar system, NASA packed the Golden Record, a playlist of Earth's greatest hits, from Bach's Brandenburg Concerto to Chuck Berry's Johnny B. Good, the selections weren't arbitrary. They were chosen for their vibrational complexity, patterns that might resonate with an extraterrestrial ear. Meanwhile, modern composers like Anna Meredith use data from solar flares to generate electronic beats, while installations like the Cosmic Bleep convert pulsar signals into immersive sound baths. Artists aren't just inspired by the cosmos, they're collaborating with it, turning raw vibration into shared experience. What's revealing is how consistently these works return to the same themes: dissonance, rhythm, and the sublime. The universe doesn't compose in major keys. It thrums with the minor tones of colliding galaxies, the arrhythmia of dying stars. When Björk sings Cosmogony or Radiohead samples Nas, a solar wind data, they're not just borrowing aesthetics, they're tapping into a primal truth. The cosmos doesn't just have music, it is music, a score written in gravity and light. And every time art echoes that truth, it reminds us, we're not just observers of this symphony. We're part of its chorus. Biocentrism flips the traditional view of reality on its head. What if consciousness isn't merely a byproduct of the brain, but the very foundation of existence itself? This radical theory suggests that the universe doesn't create consciousness. Consciousness creates the universe, vibrating into existence through an intricate dance of perception and energy. Picture a grand piano where every key represents a different state of awareness, from the hum of a single atom to the resonant frequency of a galaxy. According to biocentrism, life isn't just an accident in a cold, indifferent cosmos. We're active participants in a symphony where observation and vibration intertwine to shape reality. The idea finds surprising support in quantum mechanics. Take the double-slit experiment, where particles behave differently when observed, almost as if they choose to manifest as waves or particles based on conscious attention. Some interpretations suggest this isn't just physics. It's a clue that consciousness interacts with the vibrational fabric of reality. Even more compelling are studies on microtubules in brain cells, where quantum vibrations might generate coherent frequencies, potentially linking our minds to universal fields of information. It's as if our thoughts ripple through space-time, tuning into a cosmic Wi-Fi of shared resonance. Ancient philosophies have whispered this truth for millennia. Hindu mystics describe the universe as Nada Brahma, sound as divine creation, while indigenous traditions speak of songlines, vibrational maps that guide both land and spirit. Modern biocentrists like Dr. Robert Lanza take this further, proposing that space and time are tools the mind uses to interpret vibrations, not absolute realities. If true, death might be less like a light switching off and more like a note dissolving back into the symphony, its energy redistributed but never lost. The implications are staggering. If consciousness is vibrational, then empathy, intuition, or even telepathic phenomena could be explained as resonant harmonies between minds. Near-death experiences where patients report transcendent unity might reflect a temporary tuning into this universal frequency. Even déjà vu could be a glitch in the vibrational matrix, a momentary overlap of parallel timelines humming in unison. Critics argue this veers into pseudoscience, but cutting-edge research blurs the line. The Global Consciousness Project, which analyzes random number generators worldwide, has detected subtle anomalies during global events like 9/11 or the Olympics, hints that collective emotion might ripple through shared vibrational fields. Meanwhile, cymatics, the study of visible sound, shows how frequencies organize matter into intricate patterns, mirroring the spiral of galaxies or the branching of neurons. Coincidence or evidence of a deeper harmony? Perhaps the most poetic idea is that biocentrism reconciles science and spirituality. Meditation's calming alpha waves, the euphoria of musical free-saw, or the eerie synchronicity of meaningful coincidences, all might be glimpses of our individual vibrations syncing with the cosmos. In this view, every act of love, creativity, or curiosity isn't just personal. It's a note added to the universal composition. Whether we're temporary harmonies or permanent refrains remains unanswered, but one thing is clear: the universe isn't just something we observe. It's something we're singing into being together. In 2006, NASA Arcade satellite soared high above Earth's atmosphere, designed to listen for the faint whispers of the universe's first stars. Instead, it picked up something astonishing, a deafening roar, 6 times louder than any predicted signal. This unexplained radio wave noise, dubbed the space roar, defied all expectations. It wasn't coming from any known galaxy, star, or cosmic phenomenon. It was just there, a wall of sound saturating the cosmos, like static from an untuned radio, but on a scale that left scientists baffled. Some called it the ultimate cosmic crescendo, a mystery written in frequencies we're only beginning to decode. Theories abound, but none fully explain the roar. One leading idea points to distant, undetected clusters of galaxies, their collective radio emissions blending into a diffuse hum. Another suggests it could be the echo of primordial black holes evaporating in unison, their death throes vibrating across space-time. The most tantalizing and controversial possibility, that we're hearing the residual energy of the universe's birth, a relic vibration from the Big Bang's first moments, stretched and distorted over billions of years into a deep, omnipresent drone. Imagine catching the aftershock of creation itself, a whisper-turned scream by the expansion of the cosmos. Yet the space roar resists easy categorization. Unlike the cosmic microwave background, the universe's oldest light, this signal doesn't fade with wavelength. It grows louder at lower frequencies, a spectral fingerprint that rules out most conventional sources. Some researchers speculate it could be the collective spin of trillions of cold, spinning dust particles, their aligned rotations emitting synchronized radio waves. Others wonder if dark matter, that elusive substance shaping galaxies, might vibrate in ways we've yet to imagine, its interactions generating a faint but pervasive hum. The irony is poetic. In a universe where we've mapped black holes and gravitational waves, this simple, overwhelming noise remains one of astronomy's greatest enigmas. It's like standing in a crowded room where everyone's whispering, only to realize the walls themselves are vibrating with a song no one can identify. Future telescopes like the Square Kilometre Array may finally untangle the roar's origins, but for now, it stands as a reminder the cosmos isn't just singing. Sometimes it shouts. Imagine a planet where mountains rise and fall like the slow breath of a sleeping giant, where tectonic plates grind together in a rhythm steady enough to sustain life, but not so violent as to rip it apart. This balance, this planetary heartbeat might be the hidden key to habitability across the cosmos. We often search for alien worlds in the Goldilocks zone, where temperatures allow liquid water, but there's another critical factor: vibrational harmony. A planet's geological music, the hum of its core, the tremor of its crust, could determine whether life thrives or vanishes before it even begins. Take Earth as the cosmic maestro. Our planet's tectonic activity isn't just random chaos, it's a carefully tuned system. Volcanoes recycle carbon dioxide, stabilizing climates over millennia. Earthquakes, while destructive, release pent-up energy in measured doses, preventing catastrophic crustal fractures. Even the moon's gravitational pull creates tides that churn nutrients through oceans, fostering life's chemical dances. Scientists call this the tectonic thermostat, a feedback loop where geological vibrations regulate conditions just enough to keep the biosphere singing. Now imagine an exoplanet where this rhythm is off-key. A world with no plate tectonics might lock away essential elements deep underground, starving potential life. One with hyperactive quakes could sterilize its surface every few million years, resetting evolution's clock. The sweet spot might lie in resonance, literally. Europa, Jupiter's icy moon, flexes and cracks under tidal forces, its subsurface ocean sloshing to the rhythm of the gas giant's gravity. This constant kneading could sustain hydrothermal vents, those deep sea geysers where Earth's earliest life may have emerged. Meanwhile, Mars's stillness, its dead core, its silent crust might explain why it faded from a wet world to a barren desert. Vibrational stability isn't just about avoiding catastrophe. It's about sustaining the delicate gradients of energy and chemistry that life needs to improvise. Here's where it gets stranger. Some researchers speculate that life itself might emerge from these planetary vibrations. The panspermia theory suggests life could hitchhike on asteroids, but a newer idea, resonant panspermia, proposes that certain vibrational frequencies might actually encourage complex molecules to self-assemble. Lab experiments show that sound waves can organize particles into intricate patterns, mimicking the scaffolding of early cells. On a cosmic scale, a planet's natural hum could act like a tuning fork, guiding chemistry toward biology. The search for alien life is tuning into these frequencies. Missions like NASA's upcoming Europa Clipper will listen for the moon's subsurface song, measuring magnetic fluctuations to map its hidden ocean's depth and salinity. Meanwhile, astronomers are developing techniques to detect exoquakes, tremors on distant worlds, by analyzing subtle wobbles in starlight as planets shift and crack. A civilization advanced enough might even engineer its planet's vibrations, using artificial resonances to stabilize climates or amplify energy flows. Ultimately, the universe's most livable worlds might not just be warm and wet, they could be musical, their geology and biology harmonizing in a billion-year symphony. The next time you feel the ground tremble beneath your feet, remember, you're standing on a planet that's not just alive but singing, and somewhere out there, another world might be humming along in the same cosmic key. Neutrinos are the universe's quietest dancers, particles so ghostly, they pass through entire planets without leaving a trace. Every second, trillions of them stream through your body like cosmic whispers, unnoticed and unfelt. But here's the mystery, these phantoms don't stay the same. Mid-flight, they shapeshift between three flavors: electron, muon, and tau, a quantum waltz known as neutrino oscillation. It's as if a strawberry suddenly turned into vanilla, then chocolate, then back again, all while moving at nearly the speed of light. This isn't just particle physics being quirky. It's a clue that the universe hums with vibrations we've yet to fully hear. The discovery of this phenomenon shattered expectations. For decades, scientists assumed neutrinos were massless, like photons. But oscillations proved otherwise. These particles must have some tiny mass to perform their flavor-changing act. The implications ripple far beyond labs. Neutrinos are born in the hearts of stars, the fury of supernovae, even the Big Bang's afterglow. If they're heavier than we thought, they could be sculpting the cosmos in ways we're only beginning to grasp. Picture a universe where these invisible particles nudge galaxies into place or dark matter into clusters, their oscillations acting like a hidden conductor guiding the dance of everything. What's even stranger is how these shifts happen. Neutrinos don't just flip a switch, they vibrate in sync with quantum frequencies dictated by their mass and energy. Imagine three pendulums swinging at different speeds. Sometimes their rhythms align, amplifying one flavor. Other times they cancel out, leaving another. This interference pattern, detected in experiments like Japan's Super Kamiokande, reveals a profound truth. Even the emptiest space thrums with quantum harmonies, a subatomic symphony where particles are both notes and musicians. The most tantalizing possibility, neutrino oscillations might be tapping into dimensions beyond our own. Some theories suggest these particles could briefly wink into higher spatial dimensions. Their flavor shifts a fingerprint of unseen realms. Others propose they're interacting with undiscovered forces, like dark energy's vibrational fields. Every time a neutrino changes flavor, it's not just a particle quirk, it's a telegram from the universe's hidden layers, written in a code we're still deciphering. So next time you feel nothing but empty space around you, remember, it's alive with ghostly dancers, their silent steps shaping reality itself. And as we learn to trace their rhythms, we're not just studying particles, we're eavesdropping on the universe's oldest song. Somewhere in the vast cosmic web, hidden behind the veil of our own Milky Way, a gravitational mystery pulses with irresistible force. The Great Attractor, an unseen behemoth with the mass of tens of thousands of galaxies, tugs at everything in our galactic neighborhood, pulling stars, gas, and even entire galaxy clusters toward it at over 14 million miles per hour. But this isn't just a static pull. Scientists suspect it might vibrate, sending low-frequency waves rippling through the fabric of space-time like the bassline of a song too deep for human ears. Imagine dropping a stone into a still pond, except the pond is the universe, and the ripples distort the paths of galaxies across hundreds of millions of light years. What makes this cosmic tug-of-war even stranger is how little we can see of it. The Great Attractor lies in the zone of avoidance, a region obscured by the dust and stars of our own galaxy's disk. X-ray telescopes like NASA Chandra have pierced through this cosmic fog, revealing a sprawling supercluster of galaxies called Laniakea Hawaiian for immeasurable heaven, with the attractor at its heart. But even Laniakia's immense gravity can't fully explain the observed motions. Some theorists speculate there's something even larger behind it, a supermassive cluster of dark matter, or perhaps exotic structures left over from the universe's inflationary infancy, vibrating with primordial energy. The rhythm of this pull could rewrite cosmology. If the great attractor oscillates, expanding and contracting like a cosmic lung, its gravitational waves might imprint on the cosmic microwave background, the afterglow of the Big Bang. Future telescopes could hunt for these fingerprints, revealing whether the attractor is a fleeting density fluctuation or a permanent feature of the universe's architecture. Even more intriguingly, its vibrations might sync with other large-scale structures, forming a resonant network that guides how galaxies flow like currents in a celestial river. Here's where it gets personal. Our local group of galaxies, including Andromeda and the Milky Way, is caught in this current, destined to merge with the attractor's core in billions of years. It's a reminder that the universe isn't just expanding, it's moving, dancing to gravitational rhythms we're only beginning to hear. And as we strain to listen, we might discover that the deepest notes in this symphony aren't just shaping galaxies, they're composing the very future of everything. There's a discordant note in the cosmic symphony, one so powerful it's tearing the very fabric of reality apart. Dark energy, the mysterious force accelerating the universe's expansion, doesn't just push galaxies away. It might be vibrating space-time itself, creating a kind of anti-gravity hum that's stretching the cosmos to its limits. Imagine plucking a guitar string so hard it never stops vibrating, its oscillations growing stronger until the instrument flies apart. That's the unsettling possibility facing our universe, a crescendo of repulsion written into the laws of physics. The first clues emerged in the late 1990s when astronomers observed distant supernovae glowing dimmer than expected. Instead of slowing down as gravity pulled everything together, the universe's expansion was speeding up, as if some invisible conductor had waved a baton and commanded space itself to stretch faster. The culprit, dark energy, a term that sounds like science fiction but represents a very real, very perplexing 70% of the universe's total energy. Unlike matter or radiation, dark energy doesn't clump or fade. It's woven evenly through the vacuum of space, its density constant as the cosmos grows. The result, a future where galaxies vanish over the horizon, their light stretched beyond detection, leaving our Milky Way floating in an ocean of nothingness. But here's where vibrations come in. Some theories suggest dark energy isn't just a static force, it's a dynamic field oscillating at frequencies we can't yet measure. Think of spacetime as a drumhead. Matter and energy create dips and curves, but dark energy might be tapping out a rhythm that makes the entire surface vibrate outward. These hypothetical waves, called quintessence, could explain why the expansion rate isn't perfectly uniform. Subtle variations in the field's vibrations might cause temporary speedups or slowdowns, like a singer holding a note slightly off-key. The most radical idea, dark energy's hum, might be the echo of the universe's birth. Inflation, the explosive expansion that occurred in the first fraction of a second after the Big Bang, could have left behind residual vibrations now resonating as repulsive energy. It's as if the cosmos never stopped stretching, its initial momentum preserved in a quantum hum too faint to hear but powerful enough to shape destiny. If true, we're not just living in an expanding universe, we're riding the aftershocks of creation, carried forward on waves of primordial energy, yet mysteries abound. Why did dark energy turn on about 5 billion years ago after eons of gravity's dominance? Could its vibrations interact with dark matter, the invisible scaffold of galaxies? Future telescopes like the Vera-Rubin Observatory aim to map the universe's expansion in unprecedented detail, searching for patterns in the cosmic static. Meanwhile, lab experiments probe quantum vacuum fluctuations, hunting for hints that empty space itself vibrates with untapped energy. The stakes couldn't be higher. If dark energy's oscillations grow stronger, the universe could face a big rip, where not just galaxies but atoms are torn apart by runaway expansion. Alternatively, the vibrations might fade, allowing gravity to regain control in a future big crunch. Or perhaps dark energy is just the first movement in a longer composition, with verses we've yet to hear. One thing's certain, the universe isn't just expanding, it's singing a song of dissolution, and we're only beginning to decipher the lyrics. The first trillionth of a second after the Big Bang wasn't just the universe's birth, it was a cosmic shout that still echoes through everything. During this unimaginably brief moment called inflation, space itself expanded faster than light, doubling in size at least 90 times over. But this explosion didn't end in silence. It left behind vibrations so subtle, they might be the most important whispers we'll ever decode. These primordial tremors, etched into the fabric of spacetime, could hold answers to questions we've barely learned to ask, including whether our universe is just one note in an infinite cosmic chorus. Think of inflation like striking a bell the size of existence. The initial bang would create immediate vibrations across the bell's surface, but as the metal cools and settles, faint harmonics linger, subtle warps and ripples that tell you about the bell's material and shape. The universe works similarly. As inflation ended, quantum fluctuations' tiny jitters in energy got stretched across cosmic distances, becoming the seeds for galaxies and galaxy clusters. But some theories suggest these fluctuations weren't just random noise. They carried vibrational patterns that might reveal whether inflation collided our universe with others in the multiverse. The idea isn't pure speculation. In 2014, researchers analyzing data from the BICEP telescope thought they'd found direct evidence of these primordial gravitational waves, ripples in spacetime from inflation itself, though dust interference later clouded the discovery. The hunt now focuses on two key vibrational fingerprints. First, the cosmic microwave background, the afterglow of the Big Bang, shows temperature variations that might encode inflation's frequency spectrum. Certain spiral patterns in this ancient light, called B modes, could be the smudged footprints of gravitational waves from the universe's first violent expansion. Second, future gravitational wave detectors might catch ultra-low frequency ripples that inflation pumped into spacetime, oscillations so slow they take years or even centuries to complete a single cycle. These wouldn't just confirm inflation, they might reveal whether it was a one-time event or part of an endless cycle of universes bubbling up from a deeper reality. The multiverse connection comes from how inflation's vibrations could interact with neighboring universes. If our cosmos brushed against another during its explosive growth, the collision might have left a distinct vibrational signature, like finding a foreign fingerprint on that cosmic bell. Some models suggest these encounters could create irregular, cold spots in the cosmic microwave background or strange correlations in galaxy distributions. Others propose that different universes in the multiverse would have unique vibrational spectra, like musical instruments made of different materials. If we could read our universe's harmonics precisely enough, we might detect traces of others not as visible objects, but as resonant echoes shaping the patterns we see. What's astonishing is how close we're getting to testing these ideas. Next-generation telescopes like the Simons Observatory and CMB-S4 will map the cosmic microwave background with unprecedented precision, searching for those telltale B modes. Spaceborne gravitational wave detectors could one day tune into inflation's deepest bass notes, vibrations with wavelengths spanning the observable universe. Even tabletop experiments studying quantum materials might find analogs to cosmic inflation, recreating its physics in superconducting crystals where vibrations mimic spacetime's behavior. The implications are staggering. If we confirm inflation's vibrational echoes, we're not just learning about our universe's first moments, we're glimpsing the possible existence of countless others, each with its own laws of physics, its own vibrational song. Some might be nearly identical to ours, cosmic variations on a theme. Others could be so alien, their very dimensions vibrate at right angles to our reality. And just maybe, the reason we detect certain resonant patterns in our cosmos is because we're hearing the faint, harmonized hum of universes beyond our own, their vibrations leaking through the cracks of spacetime like sound through a thin apartment wall. The universe's first shout might have been solitary, but its echo could be a chorus. What if Earth isn't just a rock hurtling through space, but a living, breathing entity humming in harmony with the cosmos? The Gaia Hypothesis, first proposed by James Lovelock, suggests our planet functions like a self-regulating organism, where life and geology intertwine to maintain conditions for survival. But there's a deeper layer few consider. Earth doesn't just adapt, it resonates. From the rhythmic pulse of ocean tides to the electromagnetic hum of the Schumann resonances, our planet vibrates in sync with celestial cycles, as if the biosphere itself is an instrument finely tuned to the universe's symphony. Take the Schumann resonances, standing waves of electromagnetic energy trapped between Earth's surface and the ionosphere, ringing at frequencies between 7.83 and 33 Hz. These aren't random fluctuations, they're the planet's heartbeat, sustained by global lightning strikes and shaped by solar activity. Studies reveal these frequencies align eerily with human brainwaves, particularly during states of deep meditation or creativity. Coincidence or evidence of a deeper vibrational dialogue between life and its environment? Even more striking, when solar storms disturb Earth's magnetic field, the Schumann resonances spike, and so do reports of migraines, disrupted sleep, and even collective shifts in mood, as if the planet's song directly influences biological rhythms. Then there's the planet's literal music. Seismometers have captured Earth's hum, a low-frequency vibration between 2 and 7 millihertz, caused by ocean waves crashing against continental shelves. It's a sound far below human hearing, but it permeates the entire globe, a constant drone that shifts with seasons and storms. During the 2020 lockdowns, scientists detected a 20% drop in this hum as human activity quieted, proving our species' movements are woven into Earth's vibrational tapestry. Even trees participate. Research in Sweden found forests emit ultrasonic clicks during droughts, a secret language of stress signals traveling through root networks, a subterranean symphony echoing beneath our feet. The cosmos might be conducting this orchestra. Earth's axial tilt and orbital eccentricity follow Milankovitch cycles, rhythmic variations over tens of thousands of years that drive ice ages and warm periods. But these aren't just mechanical clockwork. They're vibrational patterns imprinted by gravitational dances with the Moon, Jupiter, and even the Milky Way's spiral arms. Phytoplankton blooms pulse in time with lunar tides, while some species of bacteria align their reproductive cycles with cosmic ray fluctuations. If life evolved under these celestial rhythms, is it any wonder that Earth's biosphere vibrates in harmony with them? The implications are profound. If planets have resonant signatures, could we detect living exoplanets by their vibrations? Future telescopes might analyze atmospheric oscillations or surface hums to identify worlds where geology and biology harmonize. And if consciousness arises from vibrational complexity, as some biocentrists propose, then Earth's song isn't just background noise, it's the very fabric of awareness, a shared frequency binding stone, sea, and synapse. The universe doesn't just host life, it composes it one resonant vibration at a time. As we've journeyed through the unseen symphony of the cosmos, one truth becomes undeniable. The universe doesn't just exist, it performs. Every star, every black hole, even the empty spaces between them hum with vibrations that shape the very fabric of reality. What began as ancient myths about celestial music has blossomed into a scientific revolution, revealing that the cosmos operates not just through forces and particles, but through rhythms and resonances. Pulsars beat like cosmic metronomes, black holes bellow in frequencies lower than human hearing, and dark matter murmurs in whispers we're only beginning to detect. Even time itself may be nothing more than the universe's way of keeping the beat. This isn't just abstract theory, it's a paradigm shift in how we understand existence. When Galileo pointed his telescope at Jupiter's moons, he didn't just see dots of light, he unlocked a new language of observation. Today, our instruments listen instead of look, translating gravitational waves into chirps and starquakes into harmonic scales. The result, a universe that feels less like a silent machine and more like a living, breathing composition. Einstein's vision of a cosmic symphony of strings wasn't poetic license, it was prophecy. String theory's vibrating filaments, quantum foam's ceaseless jitter, even the Fibonacci spirals of galaxies, all point to a reality where music isn't just metaphor, but mathematics. Yet the most profound realization isn't about the cosmos, it's about us. The iron in our blood, the calcium in our bones, even the electrical pulses in our brains all carry echoes of stellar vibrations. When we meditate to rhythmic tones or feel chills listening to a symphony, we're not just reacting to sound, we're resonating with a frequency older than the stars. Indigenous cultures knew this intuitively, weaving sky songs into creation myths and aligning sacred sites to celestial harmonics. Modern science is now catching up, discovering that our biology may have evolved in tune with Earth's own vibrations, from the Schumann resonances to the pull of the tides. So what's next? The frontier of vibrational cosmology stretches before us, rich with unanswered questions. Could we one day hear dark energy's repulsive hum, or decode the quantum vibrations of parallel universes? Might future civilizations communicate not with radio waves, but by strumming the strings of spacetime itself? The tools to explore these mysteries are already taking shape. LISA gravitational wave antennas, quantum computers that simulate cosmic frequencies, even citizen science projects turning backyard telescopes into cosmic microphones. As you step away from this journey, remember, the stars aren't just silent pinpricks in the night. They're performers in a grand, vibrating tapestry, and we're not just audience members, we're part of the chorus. The next time you gaze at the night sky, try listening with more than your ears. Feel the pulse of the cosmos in your bones, the rhythm of the universe in your breath. And who knows, perhaps one day when humanity finally deciphers the full score of this cosmic symphony, we'll discover that the music was inside us all along. Now it's your turn. Have you ever felt a connection to the universe's vibrations? Maybe you've heard the eerie hum of the northern lights or felt the pull of a full moon's tide. Share your stories in the comments below, and if you're hungry for more mysteries, don't forget to subscribe. The universe has countless more songs to teach us, and this channel is just getting started. Until next time, keep looking up and keep listening.